Hello everyone. Before I go forward and prove every single differential formula using limit definition, I would like to give a recap on derivatives. If you already know derivatives, you can just move forward and skip this recap. So now let's say I give you a graph that has the function y equal to x. If you want to find a gradient of this, you would use y2 minus y1 over x2 minus x1, right? You notice that when we use this formula, we get a constant integer gradient of 1, right? Here m is 1. However, when I give you, say, equation y equal to x squared, you notice that every single minute, the tangent line tangent to every single possible value of x of y equal to x squared changes for every x value. So you can't really like just plug in x and get the gradient. I mean, we would love to do that. So our goal here is using derivatives. We want to find a function for the change in the tangent line. So we use this formula which I have taught you earlier, dy over dx. Y is the limit of h approaching 0 of f x plus h minus fx over h. So now again, how, as a person who just watched my previous video on how this limit definition came about, how are you going to use this formula? So I will explain you. So let's say I give you the function y is equal to x squared. How will you use this limit definition to find a function for the rate of change of the tangent line? So let's say I give you d over dx of x squared, right? So the limit would be limit of h approaching 0 of fx plus h. Fx plus h is just x plus h squared minus x squared, right, over h. You notice that if I let h approach 0 in this case, it's a division by 0 and it's undefined. So let's expand it. You get x squared plus 2xh plus h squared minus x squared. Cancels out. And you notice that the h cancels out too. So you end up with 2x plus h. And since h approaches 0, we know that h just becomes 0. So the answer is just 2x. So what did we just find? We found a function that graphs, a function that for which every value of x you plug in, you get the gradient at the point. So let's say if I want to find the gradient at x equal to 2, I just plug in d over dx x equal to 2, which is just 2 times 2 equal to 4. So the gradient is 4. So at x equal to 2, the gradient is 4. So this is how we use the limit definition of fx plus h minus fx over h. So this is what the limit definition means. We try to find the gradient, especially when you see a very stupid graph such as y equal to x squared. So now the recap is over. Now I will try to prove one of the most basic formulas that you learn in school, and I'm pretty sure the teachers don't teach you this. So first is our favorite power rule. We know that d over dx of x to the n is known as n times x n minus 1. This is where the n is in a set of natural numbers. Okay, so how do we solve this? How do we prove this? Okay, let me try proving this. So first, we use our favorite limit definition, right? As I promised, I will be using limit definition wherever I can. So d over dx. Now in this case, dy over dx, right? So here, y is x to the n. X to the n is equal to the limit of h approaching 0 of x plus h to the power of n minus xn over h. It's similar to x squared, right? So now, this time we just can't use a quadratic formula. So we are going to use the binomial theorem. So limit of h approaching 0 is the same thing as x to the power of n plus n choose 1 xn minus 1 times h plus n choose 2 x to the n minus 2 h squared plus h to the n then minus xn. This is the same thing as you notice that the xn cancels out, right? Okay, good. So what do you notice? There's an h here, there's an h here. You can legitimately just cancel out the h, right? So it just becomes the limit of n choose 1 of x to the n minus 1 plus n choose 2 of xn minus 2 times h plus n goes h n minus 1, right? Now what happens? You notice that when you sub in h equal to 0, when you sub in h equal to 0, this entire long expression is just 0, right? So answer is just n choose 1 x to n minus 1. And n choose 1 is just n, right? N choose 1 is just n. So it's just n times x n minus 1. Here we go. We solved that. Right? Simple. So let's do product rule. So we know that the product rule is d over dx of fx and gx, right? And this is known as f prime, which is the dy over dfx over dy. So this is the same thing as df over dx, right? Here, this is just y. So it's dy over dx basically times gx plus fx and g prime. This is the formula. So how can we prove it? So now let's do it. dy over dx of fx gx. It is the same thing as the limit of h approaching 0 of f x plus h g x plus h minus fx gx over h. So what I'm going to do is pretty smart, okay? So what I'm going to do is I'm going to alter this entire expression by adding a negative fx plus h gx plus gx fx plus h, okay? It's just nothing. This thing is just 0. But I'm just going to add them in. Now, I'll try to split the entire limit. So, I think I'll need more space. So, limit of h approaching 0. Now, it's just fx plus h gx plus h minus gx over h, right? And this is the same thing as gx is fx plus h minus fx over h, right? This makes sense, right? If you combine them together and you expand it, you notice that it's just negative fx plus h gx plus gx fx plus h, right? It just cancels out. We are splitting this integrand, we are splitting this function into two different limits, so it's easier to solve. So now what do you notice? This entire thing is what? This entire thing, g x plus h minus g over x. This looks like g prime, right? Looks like d g of x plus h over dx, right? Right. Similarly, this thing looks like f prime, right? Doesn't it? So now we are going to collapse it again. This is the same thing as f x plus h times g prime plus gx times f prime. And now since h approaches 0, it's just fx g prime plus gx f prime. Yeah, we've solved it. This is pretty intuitive, right? So now let's solve the next one. Quotient rule. So the quotient rule is where, say, we differentiate d over dx of fx over gx. This is the same thing as what? F prime times gx minus fx g prime over g squared x. So these formulas that I'm listing, quotient rule, this is what, the product rule. These are just formulas that is so much easier to memorize. So think about it. Imagine that you have this fx and gx and you want to plug it straight away into the limit function, limit derivative function. It's so much harder, right? The limit definition is just so much harder to approach, and sometimes the expansion might get harder. So instead, we use this simplified version of these formulas, which is easier to, solve in to differentiate functions in general. So now what we're going to do is we're going to express this y. Let's say this entire thing is a y, okay? Y is the same thing as well, fx times g to the negative 1, right? Makes sense, right? And now when we do dy over dx, we're going to use product rule. What is the product rule? We're using this rule here, right? This is again very simple. I mean, we can try using the limit definition, but I'm pretty sure it will be very, very tedious. So here we take the derivative of fx with respect to x and we leave this the same. And now we use fx times negative 1 times g to the negative 2 times x. G to the negative 2x and g prime. What are we doing here? We are using something called the chain rule. I'll be proving this identity later. So what we do, whenever you see a composite function, say f of gx, and we try to differentiate it, we get f prime of gx times g prime. There's just a notation. When we use primes, it's just a notation. Okay, so now what we're going to do is we are going to express this as f prime over gx minus fx g prime x over g squared x. I'm going to multiply here by gx, here by gx. Now this is the same thing as f prime x gx minus fx g prime x over g2x. We proved it. So now we have proved every single identity. I think I'll leave chain rule for another video. Thank you.